Welcome to lecture number 24 of my series on classical thermodynamics. Over the last two lectures, we have been discussing the stability of thermodynamic systems, and in today's lecture, I was supposed to continue on the same theme. However, during the preparation of this lecture, as well as during the delivery of the previous one, I realized that I had made a rather serious omission in this series. During thermodynamic calculations, one thing that we often need to do is reduce derivatives. That is, in practical applications of thermodynamics, we often have to evaluate a wide class of partial derivatives and try to reduce them in terms of simpler forms. We had done that in the last lecture when we talked about Cp minus Cv, the difference between the heat capacities, or kappa T minus kappa S, the difference between isothermal and adiabatic compressibilities. We have managed to reduce them to simple expressions, and indeed what we will find is that all derivatives in simple systems at least can be reduced to three basic derivatives apart from other extensive or intensive state functions. Now the set of three derivatives essentially is arbitrary, not completely arbitrary, but at least is something which you can choose on your own, but we usually choose a set of three given by small cp, which of course is defined to be T del S del T at constant P and N, the heat capacity, or rather the molar heat capacity at constant pressure, alpha, the volume expansivity, defined to be 1 over V del T at constant P and N, and kappa T, the isothermal compressibility, defined as minus 1 over V del P at constant T, N. Let me remind you that the minus sign here is basically to ensure that kappa T works out to be positive. And we have already seen from stability considerations that out of these three quantities, Cp and kappa T are guaranteed to be positive for stable systems. Alpha can be either positive or negative. It's usually positive, but there are systems in which increase in temperature causes a decrease in volume. Water between 0 and 4 degrees Celsius being a very, very important example. So you can have alpha which is negative. Now the reason why we want to reduce all our partial derivative calculations to say this particular set of three partial derivatives or three physical quantities is that these three are actually often rather easy to measure experimentally. So it would be very easy if we were to express our partial derivatives, which would usually express experimental or experimentally relevant quantities, in terms of these three, then we should be able to match with experimental values rather nicely. So that is the reason why we actually look at these three quantities and try to express all our partial derivatives in terms of these three. Now, what I'm going to do today is follow Callen's book, Callen's wonderful book, Thermodynamics and an Introduction to Thermostatistics. In fact, I have actually followed Callen to some extent when we talked about stability in the last two lectures as well as in a previous lecture when I talked about releasing of a constraint in a closed system. Callen, of course, is a wonderful book. It is not really that suitable as a textbook for, say, a standard BSc course in an Indian university, for the simple reason that Callen happens to have an entirely independent, logically complete, and near perfect exposition of thermodynamics, which is different from all other expositions and typically different from what you would find in your textbooks. So if you are a beginning student of thermodynamics, I would first suggest that you read your textbooks, and then once you have got a grasp of what they are trying to say, definitely read Callen. So let me just write down the name of the textbook for you. It's H.B. Callen, Thermodynamics. I'm just repeating the name again. And an introduction to thermostatistics. I'm going to borrow heavily from Callen's book today, simply because Callen gives a very, very systematic procedure for reducing partial derivatives to these three quantities in the end. It's a sure shot procedure which is guaranteed to work. I'm pretty sure that many of you who have done thermodynamics courses would have carried out similar calculations, but the advantage of Callen's method is that it gives you a step-by-step procedure which is going to work without leading you into false steps. So let me now describe Callen's procedure to you and also illustrate that with a few examples. But before I outline Callen's systematic procedure, let me gather together all the mathematical tools that we are going to need for this. They come essentially in three different classes. The first one of these are basically properties of partial derivatives. These are things we have already derived before, and they are part and parcel of any standard mathematics course. Let me just collect those that we are going to need here. One of them, a very obvious looking one, is that del x del y and del y del x are reciprocals of each other, where x and y are any two functions, as long as you are carrying out these partial derivatives holding the same quantity z constant. So as long as the same z is being held constant, these partial derivatives essentially behave the same way as ordinary derivatives do. The second property is also something that is similar to what ordinary derivatives obey. This is a sort of chain rule, so to speak. Del x del y at constant z is the same as del x del w at constant z divided by del y del w at constant z. This can of course also be written as del x del w at constant z times del w del y at constant z. And while I know it's sacrilege to say that a derivative is like a ratio, after all there is a limit involved, a very quick way of remembering this would be that if you were to think of this like a ratio, the del w's would just sort of cancel. Now the important point here is that this will work as long as the same quantity z is being held constant in each of these derivatives. If that happens, this is basically similar to the way you do ordinary derivatives. But the difference becomes starkly clear when we look at the last of the important properties. Again, a property that we have already derived before. This again talks of del x del y at constant z, but now it relates to derivatives, these two derivatives, which involves z, the quantity which is being held fixed here. So you get del x del z at constant y over del y del z at constant x. Once again, if you use this crude analogy between a derivative and a ratio, the del z's seem to cancel. But what is extremely important here is that the same quantity is not being held constant. You have three variables x, y and z. Here, x is being partially differentiated with respect to y with z constant. Here, you are holding y constant, doing del x del z. Here, holding x constant, doing del y del z. And the result is not the same as what you would get by a mere cancellation. You have an extra minus sign. Of course, this also can be written down in the form minus del x del z at constant y times del z del y at constant x, or as minus del z del y at constant x divided by del z del x at constant y. This last version, in which z goes in the numerator, so to speak, of each of these partial derivatives, actually happens to be a very useful version for us, and it's going to be used several times in our examples. So these are the three basic properties of partial derivatives which we will need to invoke again and again when we reduce our partial derivatives to this final reduced form involving kappa t, alpha and Cp. Now these were inputs basically from mathematics, general properties of partial derivatives. The next set of inputs come from thermodynamics. It deals with thermodynamic potentials and Maxwell's relations which follow from them. Again, these are things which you have already derived before, but let me just quickly recapitulate them for you. The four important thermodynamic potentials that we talk about are internal energy, enthalpy, Helmholtz free energy and Gibbs free energy. And internal energy, for example, for a simple system obeys du is Tds minus Vdv plus mu dn. And so, of course, T is del U del S at V and N fixed, minus P is del U del V with S and N fixed. And because of the equality of mixed partial derivatives, if you were to differentiate del U del S with respect to del V and del U del V with respect to del S, you would get the same result. And this gives us Maxwell's relation number 1. Derivative of this quantity with respect to this variable is the same as the derivative of this quantity, in this case minus P, with respect to this variable. That is, del T del V with S and N fixed is the same as minus del P del S at constant V and N. Now H is obtained from U by adding PV, and that tells us that dH is Tds plus Vdp plus mu dn, and using the same argument, what we get is del T del P at constant S and N is the same as del V del S at constant P, N. Now these are the Maxwell equations, in the two of them, and these two equations contain S in the denominator. Even more useful for our purpose would be ones which contain S in the numerator, the ones which you obtain from dF and dG. F is U minus Ts, so minus SDT minus PdV plus mu dn. And once again, you can easily see that this tells us del S del V at constant T and N is the same as del P del T at constant V and N. Now this one is actually pretty useful because it allows you to relate a derivative of the entropy with something you can calculate from a mechanical equation of state. G, which is U minus Ts plus Pv, has a differential minus SdT plus Vdp plus mu dn, and that also tells us that del S del P at constant T and N is minus del V del T at constant P and N. Now you can actually have other ways of remembering Maxwell's relations. There are many different mnemonics available, but I find the mnemonics actually more difficult to remember. As far as I am concerned, it's way easier to start with du is Tds minus Pdv plus mu dn and derive the Maxwell's relations just by using the kind of argument that I have given here. Well, we did not involve derivatives involving mu in this, which we could have by, for example, this du is Tds minus Pdv plus mu dn would have told you that del mu del S at constant V and N is the same as del T del N at constant S and V and so on. But we will not really focus on derivatives involving mu because we have one more relation, the third category, which also follows from thermodynamics, which hinges really on the fact that U is an extensive function of its three arguments, which are each extensive. This gives rise from Euler's equation in mathematics of this famous Gibbs-Duhem relation, that U is actually equal to Ts minus Pv plus mu n. And that means, of course, that du is Tds plus sdt minus Pdv minus Vdv plus mu dn plus n d mu. And since Tds minus Pdv plus mu dn is already known to be du, this immediately gives us a differential form of the Gibbs-Duhem relation, sdt minus Vdv plus n d mu equals 0. This relates the d mu to the other derivatives. So whenever you have derivatives involving mu, you can actually invoke the Gibbs-Duhem relation to rewrite this in terms of the other derivatives. Which is why we did not really bother to write down Maxwell-like relations involving mu's partial derivatives. So these three kinds of mathematical relations: one, directly mathematical, these conditions within partial derivatives; the second set, the thermodynamic potentials, differentials, and the Maxwell relations which follow from them; and finally the Gibbs-Duhem relation. These are the arsenal that we are going to need in order to reduce partial derivatives into a final small set of experimentally measurable objects. So let me now outline Callen's procedure step by step. The first step, according to Callen, would be, if there are potentials, that is thermodynamic potentials in the derivative you want to calculate, then bring them to the numerator and evaluate the derivatives basically using the expressions for du, dh, df, dg, whichever may be relevant. Now just to illustrate this, let me talk of a physical process which is actually very, very important, especially important in cryogenics, because this process is used to produce low temperatures. For cryogenic experiments, this is called the Joule-Thomson process or Joule-Thomson throttling, where what you do is basically the following. You have a porous plug with a gas on one side of it. The gas is being pressed in through a movable piston by a pressure P1. The pressure of the gas inside is almost P1, just slightly less, so the piston actually moves in. And at the beginning, there is another piston on the other side of the porous plug being pressed here onto the porous plug by a pressure P2. And typically P1 is more than P2, which makes the gas actually push through the porous plug and push back this piston. So once this procedure is completed, all the gas from the left-hand side of this porous plug has been transferred to the right-hand side. Of course, it's now at a different pressure, so it would typically have a different volume as well. Whether it will be a lower volume or a larger volume will depend on both the equation of state, the temperature which it reaches at that point, as well as typically the pressure head that you have, the difference in pressures. Now, this whole thing is supposed to be enclosed in an adiabatic environment. No heat can flow. Now look at what the net work done on the gas is. On the left hand side, you have this piston pushing in the gas and doing positive work on the gas. How much? That's simply P1 times V1. It's actually P1 times delta V, but you had V1 volume to begin with, 0 volume at the end here. So P1 times V1 is the work that was done on the left. But the gas, in pushing back this piston, has actually done positive work on the piston, which means negative work has been done on it. And how much work has been done here? P2 times the change in volume on this side, which is of course P2 V2. So net work done on the gas, this is on the gas, W is P1 V1 minus P2 V2. But note that here the heat flowing in is 0 because the whole thing is in an adiabatic enclosure. Therefore, the change in internal energy delta U is simply Q plus W. The heat flowing in plus the work which is being done on the gas. And therefore, you can rewrite this as U2, where U2 is the internal energy of the gas after it has crossed through the porous plug, minus U1, the internal energy before on the left hand side, is simply equal to W, which is P1 V1 minus P2 V2. And that tells us that if you compare the enthalpies before and after this process, you get the same value. H1 is the same as H2. Now, we often hear that the Joule-Thomson process is an isenthalpic process, a process at which enthalpy is held constant. But that really is not the correct way to put it, simply because this is a non-equilibrium process and there is no guarantee that the enthalpy will necessarily be the same as the initial value. In fact, will even be defined during the process. What you really know is at the end and at the beginning of the process, you have two steady states, two equilibrium states which have the same enthalpy. However, that is enough to ask and answer a very important question. This whole process, as I said before, actually is used to cool down gases by this throttling process. Now, there is a pressure change which takes place. Corresponding to this pressure change from P1 to P2, with H1 and H2 being the same, the question that we have to answer is, how are the two temperatures related to each other? This will tell us whether we can actually cool the gas or not by doing a Joule-Thomson throttling. And there, what we see is the following. We need to calculate this particular coefficient called the Joule-Thomson coefficient, del T del P at constant H and N. In fact, I have mentioned N throughout here, but N is a constant in the whole process, so we can sometimes drop the N with the secure in the knowledge that N is not going to change in the whole process. This quantity is all important in deciding whether Joule-Thomson throttling will actually cause cooling or not. If this is negative, then an increase in pressure will cause a decrease in temperature. But during throttling, it's really a decrease in pressure. P1 is typically more than P2. So you need mu Jt to be positive in order to get a cooling by Joule-Thomson process. Now, this is our first example of a partial derivative that we are going to reduce using our procedure. And notice that step 1 is that if there are potentials, thermodynamic potentials involved in the derivatives, you have to bring them to the numerator and then evaluate using the standard differentials of those thermodynamic potentials. So, notice that you do have a thermodynamic potential here, H, but H is not in the numerator or the denominator of this partial derivative. I will not apologize for using the words numerator and denominator here. I hope all of you understand what I mean. It is actually sitting in the term which is being held constant, which is why we have to use the third property of partial derivatives, which actually brings in the H in the derivative. Well, you can rewrite this as del T del H at constant P comma N by del P del H at constant T comma N, but at the expense of a minus sign. Or because we want the H in the numerator, it's best to rewrite this as a reciprocal of itself upstairs. So this becomes del H del P at T comma N by del H del T at P comma N. Now, because we know that H has the differential dH is TdS plus VdP plus of course mu dN, but that term vanishes anyway because N is being held constant. Let's see what this becomes. The del H del P at constant T comma N simply reduces to T del S del P at constant T comma N plus V. Of course, the mu dN term vanishes. The denominator simply becomes T del S del T at constant P comma N. Since P is held constant here as well, the VdP term goes away. So you don't have any contribution from the VdP in the denominator. Of course, you have this minus sign, which is just this minus sign sitting here. So that's our step 1 done. We have managed to get rid of all the thermodynamic potentials that we had in this case only one of them, H, and have expressed their derivatives in terms of other variables. Now step 2. This is step 2 according to Callen, and this is the step that we should have to do at this stage, which is if the derivatives that we have to deal with involves mu, the chemical potential, then you have to bring it to the numerator and eliminate it simply by using Gibbs-Duhem relation. That is, use d mu. Remember, we had n d mu, so when you write d mu, you are dividing through by n. It's minus small s dt plus small v dt. These are molar entropies and molar volumes respectively. Now, this particular step is not relevant for us because our derivative at this stage does not contain any mu anywhere. Neither in the numerator nor in the denominator of any partial derivative nor in what is being held constant. So this is a step we will skip for this particular calculation. Now step 3. This is of course very important. We will bring S entropy now to the numerator if it's not already in the numerator, and then use Maxwell's relations to reduce them. Sometimes you will end up with del S del T, which cannot be reduced using Maxwell's relations. There, what you do is essentially supply a temperature T and write T del S del T, and that will give you either Cp or Cv depending on what is being held constant in this partial derivative. So that's how you tackle the entropy derivatives. So take a look at our statement here. We have reduced our del T del P at constant h, n, the expression for mu jt, to a ratio of two terms, each of which involve derivatives of s. But notice now that in the denominator, we have a del S del T, something which cannot be reduced using Maxwell's relations. Remember, Maxwell's relations only relate coefficients of one term differentiated with respect to the variable in the other term. T and S are always in the same term, either T ds or S dt. So Maxwell's relations will never have a del S del T or del T del S. But, as we have said, that's not a problem. T del S del T at constant P, n. Here we did not have to supply an extra T because it's already there. This is nothing but heat capacity at constant pressure, capital N times small cp. Small cp is the molar heat capacity. But this del S del P at constant T, n is something you can reduce using Maxwell's relations. Now, if you want to do this kind of calculation regularly, it would be a great idea to memorize all of the Maxwell relations, or at least remember one of the mnemonics available which can help you figure out what the relevant Maxwell relation is. However, as I have already said, I can't remember the relations, but I do remember how to derive them. So let me just point out that I would approach this in the following manner. I need a relationship involving del S del P at constant T. And this fact that you are differentiating S shows that we have to look for S dt in the differential of whatever thermodynamic potential we are looking for. And the fact that you are differentiating that with respect to P would mean you would need a dP here. And so, of course, that should come with a V. Now, S dt is something which comes with a minus sign because T ds has a plus sign as far as du is concerned, and vdp by the same token comes with a reverse sign of T dv, so has to come with a plus sign. Now this of course is nothing but the differential of dg, except for the fact that I have not bothered to write down the mu dn. Be that as it may, the moment you figure out that this has to be the differential of some function of state, it immediately tells you that the derivative of this with respect to this, holding t and the n I have not mentioned, fixed, that is minus del S del P at constant t comma n, must be the same as the derivative of this quantity V with respect to this variable holding P and n fixed. So, has to be del V del T at constant P comma n. So, this derivative sitting here is minus del V del T at constant P comma n. We can of course take this minus sign inside the numerator, and that will make this expression T del V del T at constant P comma n minus V for the numerator. The denominator, as we have already seen, is NCP. So this concludes step 3, getting rid of the entropy from our expression. Step 4 actually involves the volume, and it says that you have to bring the volume to the numerator of the partial derivative. In all of these cases, when we are saying numerator or denominator, we usually mean what is being differentiated in a partial derivative as opposed to what you are differentiating it with respect to. In this case, you don't have to bring the volume to the numerator because it's already in the numerator, so to speak. And then what you can do is express the derivative in terms of alpha and or kappa t. Now, how do we do that? Well, in this case, it's pretty straightforward. 1 over V del T at constant P comma n is alpha. So this really is the same as V times alpha, this partial derivative. So if you just put that in, you get the following result. Del T del P at constant H comma n, our mu Jt, the Joule-Thomson coefficient, works out to be V over Np. I've just shown you the place where the alpha emerges here. And then, of course, there's a t which I forgot to write down in this case. Minus 1. And now, by replacing 1 by V del T by alpha, we end up with the expression capital V by NCP alpha t minus 1. Actually, I can reduce this a bit further. It's really not a big reduction. But now we can see that this quantity, which after all is a derivative of an intensive variable with respect to an intensive one, is actually intensive. And you can see that explicitly by seeing that this is small v alpha t minus 1 by Cp. Small v being, of course, the molar volume. So this actually concludes the reduction for us. We have managed to express our quantity of interest, the Joule-Thomson coefficient in this case, in terms of the molar volume and temperature, which is of course a function of the state involved, and the expansivity and the molar heat capacity. Now there's one more step in this whole procedure, which is no longer necessary here because here our reduction is already complete, as we have said. But sometimes it might so happen that the derivative that you end up with of S, which is a T, is done at constant volume and not at constant pressure. So this would have given you small cv instead of small cp. If you insist on writing everything in terms of alpha, cp and kappa t, then what you would have to do is eliminate cv in favor of cp by using a result that we have already seen before. This result, of course, only uses cp, alpha and kappa t other than variables which describe the state. So this would actually convert any expression which has a cv and maybe also cp, alpha and kappa t into an expression which has only cp, alpha and kappa t. Now this final state may sometimes be carried out, sometimes you may not bother to do it, but if you insist on writing everything in terms of these three parameters, cp, alpha and kappa t, then this step has to be carried out. So we have shown one complete example of the reduction of a relevant physical derivative in terms of three easily experimentally measurable quantities. Now this was a particularly simple example, as such examples go. So what we are going to do next is to illustrate the procedure in full once again by carrying out the calculation of a much more complicated derivative. Now, the only reason why I have chosen this particular derivative is that Callen actually uses it in his book to illustrate his step 1. I will actually go through with the whole calculation, unlike what Callen has done. I'm pretty sure Callen has not bothered to carry out all the 5 steps using this particular derivative, simply because this particular derivative may not be that relevant as far as a physical application is concerned. So he did not bother. I'm just showing you the calculation of the reduction to the final step simply because I want to illustrate Callen's 5 steps one by one. So the partial derivative that we are going to calculate now is the derivative of pressure with respect to internal energy holding the Gibbs free energy and the number of moles fixed. Once again, I don't really know whether this has any practical application. I'm just showing this as a way of illustrating the procedure. Now, step 1, remember, was you have to take any thermodynamic potential available here to the numerator and then reduce it using the differentials of the thermodynamic potentials that we have. Here there are actually 2 thermodynamic potentials in view. There's U here, which is in the derivative itself, and G, which is being held constant. Now we need to actually bring both of them to the numerator, so to speak. And let's do that one by one. The first step, of course, is to rewrite this partial derivative as a reciprocal of del U del P at constant G, N. In this form, U is in the so-called numerator, and starting from du is TdS minus PdV plus mu dn. It's easy to see that this derivative is T del S del P at constant G, N minus P del V del P at G, N, of course the reciprocal of this quantity. The third term mu dn does not contribute because this is being done at constant n. So dn is 0. Now, the next step would be to check that we have not really got rid of all our thermodynamic potentials. Capital G is still there. So we have to bring the G to the numerator. And the trick that we will use here is using that property of partial derivatives, which helps us to cyclically go through 3 functions. So you have S's derivative with respect to P at constant G. We will change that to del G del P at constant S, N by del G del S at constant P, N. Once again, this looks a bit like the derivative where the G would tend to cancel out, but at the expense of a minus sign. So this is minus T del G del P at S, N by del G del S at P, N. The same thing is done here. You write this as del G del P at V, N by del G del V at P, N. The minus sign, of course, couples with this minus to make it a plus. Now we are in a position to use dg. dg, remember, is minus S dt plus V dP plus mu dn. Once again, the mu dn term is not going to contribute because these derivatives are all carried out at constant n. But let's see what the rest will tell you. Del G del P at constant S, N will give you minus S del T del P at constant S, N. The other term, of course, will be there, but that will be simply V. Del P is 1. And del G del S at constant P, N will be much simpler. S del T del S at constant P, N will be 1 term. The VdP term and the mu dn term will not contribute because P and N are held constant. Similarly, we can calculate the ratio here, and once we put everything in, these are the 2 terms you get. The first one essentially comes from reducing this numerator to this one and this denominator to this. These are, of course, real numerators and denominators, this being an actual ratio. And from the other term, you get this term gives you this, and del G del V at constant P, N. Once again, the VdP term drops off, being done at constant P, and gives you only 1 term. So we have carried out our first step completely. The first step, remember, involves getting rid of all the thermodynamic potentials by bringing them to the numerator of the partial derivatives involved and carrying out the partial derivatives using the differentials of the thermodynamic potentials that we already know. Now for step number 2. Step number 2, once again, is not relevant here. This is not being done in a way in which mu is involved anywhere, either as the differentiator or the differentiatee or the term being held constant. So you don't have to carry out step 2 here as well. So we come to step 3. And step 3 involves bringing all the entropies which are involved in the partial derivatives to the numerator and then using Maxwell's relation. So let's see how the first term here fares. Del T del P at constant s comma n of course becomes del s del P at constant t comma n by del s del T at constant p comma n at the expense of a minus sign. But here what we have done is we have gotten rid of this minus sign in expense of this. Of course, this minus sign has been brought in to make this plus to begin with and this one minus, and the minus sign from the partial derivative formula comes in here and you have a minus v. And here in this term you can easily see that the job of bringing the s to the numerator can be done very easily by just using the reciprocal. So this is just del s del T at constant p comma n. This s, the minus s, goes here. A very similar thing is done for the second term. This minus s comes here. Del T del P at constant v comma n, we leave it as it is. There is no s involved here. Here too there is no s involved. So there is nothing further to be done as far as this step is concerned here. So what we need to do is simplify this by either using Maxwell's relations, or if the derivative involves a temperature of entropy, invoking the formula for Cv or Cp. Now that's pretty straightforward. Del S del P at constant t comma n, we have already seen this just a while ago, is minus del V del T at constant p comma n. So we plug that in. This T del S del T at constant p comma n is actually small cp times capital N. So we write that. We have brought this minus s in, so we cancel this. This becomes plus v by s. And this del S del T at p comma n in the numerator of the first term has to be supplied by the temperature. So if we put in a 1 by T here, then we get T del S del T at p comma n is ncp. We just plug that in. As far as the second term is concerned, there is of course nothing much to do except cancelling out the minuses by bringing it in. So you end up with this expression. This just becomes del T del P at constant v comma n. This term becomes minus v by s. So step 3 is complete. You must have realized that I have written all the things that we have done in step 3 in this purple color, whereas the step 1 was in red. There was no step 2, so there is no color for that. Now we switch colors once again because we want to go on to step 4. Step 4, remember, says that we bring all the volumes to the numerator and then evaluate those partial derivatives either in terms of alpha or kappa t or both. So, what is there to be done in this whole case? Notice we have ncp into v by s, that's of course this term. This minus del v del T at constant p comma n, v is already in the numerator here, and if you supply this with a 1 over v, so v times 1 over v, then this becomes alpha. So this whole thing is minus v capital T alpha by ncp once you simplify this. The first term was pretty straightforward. Let's go to the second term. Here del T del P at constant V comma N has V in the constant term. That thing being held constant. We have to bring it into the partial derivative itself. And for that, we use our very familiar formula by now. Write this derivative del T del P at constant V comma N as minus del V del P at constant T comma N by del V del T at constant P comma N. There's a minus V by S sitting outside. And you have del V del T at constant P comma N there, which of course cancels out this particular denominator. So you just have to worry about minus del V del P at constant P comma N. And once again, you just apply it with a 1 over V by multiplying it, of course, by 1 over V times V. Then minus 1 over V del P at constant T comma N is nothing but kappa T, the isothermal compressibility. So the second term simplifies, so this is the second term here, to V times kappa T, this of course cancels, minus V by S into del V del T becomes minus V square by S into alpha, simply because to convert this to alpha you need a extra V. So this is your derivative. Let me just simplify this slightly by bringing the capital V which is there in every term out and expressing whatever is in there in terms of molar quantities. So once I take the 1 over V out, remember the V comes out, but this is already in the denominator. There's a minus 1 power here, so that's why what is coming out is 1 over V. Now what we get is small Cp, capital S by N is small s, so molar entropy, minus T alpha, plus P kappa T, minus P with the loss of 1 V. This is capital V over capital S, and by dividing both the numerator and the denominator here by capital N, we get small v by small s. Molar volume by molar entropy into alpha. Now a quick check of whether this sort of makes sense. The whole expression here, which is in the denominator, turns out to be an intensive variable because it's composed entirely of intensive variables. And the overall thing is a 1 over v. So this is really the reciprocal of an extensive variable. Let's just check whether that is what we expect. If you look at your original derivative, the one we are trying to reduce, we are actually doing a derivative of pressure with respect to energy. That of an intensive variable with respect to an extensive variable. You do expect the overall derivative to be the reciprocal of an extensive variable. So at least that part is right. Of course, that's no guarantee that we have done all the steps correctly. So I would urge all of you to check whether this is correctly done, especially all the signs are correct as they stand. But I do think I've managed to illustrate the procedure sufficiently for you to be able to carry out further reduction of derivatives on your own from now on. And let me just point out once again, for specific derivative reductions, it may be possible that if you do not stick to this particular 5-step process, but use your own set of steps, you might be able to get to the answer more quickly. But that will happen only in very special situations. The beauty of this 5-step procedure is that this always works, and as long as you're careful about the signs and so on, it will never lead you astray.